And we're back. We are officially done doing proofs with quantifiers and inequalities, or I should say, we are done going over these in class. You're probably still going to have to do these on quizzes, and you're definitely going to still have to do these on assignments. But things are about to get a bit easier from here, and starting next Monday, things will be getting a lot more computery. But for now, we're going to keep looking at asymptotic notation and learn some techniques for reasoning with these that are a lot easier than working with the definitions. So say we have a statement like n to the 4 plus n is in big O of n to the 6. This looks true because of the differences in exponents. You could probably prove it with like the rounding up trick or something. But if you have more general statements that hold for all functions, you could skip a lot of that mechanical work and honestly skip a lot of the creativity and make a really well-functioned or well-structured argument that shows that the statement is true. So statements A and B are both true facts. One is that for any constants B and A, where B is greater than or equal to A, NA is in the big O of NB. So that's saying stuff like n is in O of n squared, n is in big O of itself, n to the power of 0.0001 is in big O of, I don't know, I'm not going to write any exponents here. I've already run out of space. Note that these exponents both have to be greater than 0. This doesn't say anything about negative exponents, and an exponent that is exactly 0 is just 1. But it's a good fact to know. And we have an addition rule. So if f is in O of h and g is in O of h, then the sum of f and g is in O of h. So going from these two facts up here, actually no, I'm going to make two new ones. So n is in big O of n squared as before. N squared is in big O of itself. Remember, big O is like less than or equal to. And those two facts you can use together with fact B to say something like n squared plus n is in big O of n squared. It's an addition rule. There's going to be at least one question in a future assignment that asks you to prove that this like huge polynomial with a whole bunch of terms is in big O of n to the something. I don't know, maybe it was 6. And it would have been a humongous pain to prove with the definition. But with this rule, you can split it up into more manageable proofs for each term, and then use the addition rule to put it all together. So again, suppose that we know that these are true. Now we have the ability to make a much shorter proof of the fact that n to the 4 plus n is in big O of n to the 6. I kind of already did something like that with my example of how n squared plus n is in big O of n squared. So by property A, we know that n to the 4 is in big O of n to the 6, and that n, which is, as you know, secretly n to the power of 1, is also in big O of n to the 6. that property at the top of the slide sort of formalizes the trick I told you earlier about how you could tell which function probably grows faster by looking at the exponents. So we've proven these two things, and now we can just add the function. And since we both, or add the two functions together. And since we know that both of them are in big O of n to the 6, their sum is also in big O of n to the 6. Done. Wasn't that so much nicer than using the definition? What follows in these slides are a few proofs of general properties, but I'm going to skip over them, at least for now, partly because the quiz takes up like a 45-minute chunk of class time, but also because I want to make sure the class's content and evaluations are in sync with each other, and you're never really going to be asked to do anything like this. There will be proofs of general asymptotic properties from the definition in a bonus question on the last assignment. And I don't think this is the time to be worrying about a bonus question on the last assignment. So skip. And now we'll do some more examples of the sort of new way to prove statements about asymptotic notation. In assignments, you'll be told whether to use the definition, whether to use these properties, and whether to use a secret third method that I'm not going to tell you about, but it's going to be in an optional reading next week. So I'm going to pull up the readings. I think I'm going to have to go on UMLearn for this. I have the slides in cloud storage, and oh, no, don't call me. No. Okay. Wait for it. There we go. By the way, if you have an Apple device, or if Android and Windows devices working together let you do this, highly recommend using the text message verification, because it lets you just tap to autofill the code from messages. It's nice. Hopefully we still get enough space to look at all these after splitting the screen. Phew. Okay, so these definitions will show you, or these demonstrations are going to show you the workflow for proving statements in this way, and basically what you'll do on assignments and at least one future quiz. Oh, and another thing before we begin, this is a lot of facts. You shouldn't put like a deliberate effort into memorizing these, but if you use them enough, you'll just sort of develop an intuition that includes all of these facts. A question like this will most likely appear on a future quiz. And when that happens, I'll just give you all of the relevant facts, plus a couple red herrings. So like there will be 5 facts or something like that taken from throughout this document. All right, enough chit chat. We're going to prove that n plus 1 is in little o of n cubed. So by fact 1.3, which is, oh, I wish I could underline stuff on the PDF too. Oh well. Yeah, I'll just say the numbers and you'll have to keep up with it. Fact 1.3 is very similar to the fact that we went through earlier in the slide. Basically, polynomials can be ordered by their exponent. And by this, we know that n is in little o of n squared. Notice that the fact uses a strict inequality. So n isn't in little o of itself, but it is in little o of n squared. And then we use fact 1.1 to show that a constant 1 is in little o of a logarithm. And then by 1.2, we take that logarithm and show that it's in little o of any polynomial. In this case, n squared, because that's the one we're looking at. So the constant 1 is in little o of that logarithm, which is in little o of that polynomial. By transitivity, 1 is in little o of that polynomial. So now we know n is in little o of n squared, and 1 is in little o of n squared. And then we could use the addition rule to say that n plus 1 is in little o of n squared. Just a note on notation. I was talking about how 1 is in little o of whatever. When I say stuff like that, I'm not talking about the number 1, but rather the function that takes an input n and just returns 1 for any input, a constant function. All right, n cubed is in big O of n cubed plus 1. Very similar structure, very similar statement, but we're going to go about it in a different way. Actually, I shouldn't say very similar statement. The fact that the thing with two terms is inside of the asymptotic notation thingy does change how we have to approach it quite a bit. But the change that it makes in our approach is just a matter of changing the question so that we could use the old approach. So fact 3.2, can I zoom in? Yeah. Says that f is in big O of g. Remember, these are short forms for f of n is in big O of g of n and stuff. If and only if g is in big omega of f. Well, that's cool. This is sort of an example of what I said earlier about building an intuition for these things. I think that this list of properties, as you keep using it and using it, will definitely help your understanding of what these things even mean. Because I bet in the lecture after I just told you the definitions, you probably wouldn't have been able to figure out that f is in big O of g if and only if g is in big omega of f. But after seeing it, after using it, you'll probably understand it quite well. Okay, so we find that n cubed plus 1 is in big omega of n cubed if and only if n cubed is in big O of, yeah, I guess what I'm saying is correct, just structured badly. If and only if n cubed is in big O of n cubed plus 1. So we sort of flipped it around. Now we have a thing with two terms on this side and a thing with one term inside of the asymptotic notation, which makes this look basically identical to the thing we just proved. On step 2, I'm pretty sure it's the case that for exponents a and b such that a is less than or equal to b, we'd have a result about n to the a being big O of n to the b, and thus we'd be able to change that to big omega. But while this appears on the slides, like this was the thing that showed up at the beginning of the lecture. Actually, I'm just going to make sure. Ugh. Oh yeah, totally. That non-strict inequality let us use the big asymptotic notation. Anyway, I don't think this fact shows up on this sheet, so we're going to take a slightly different approach. Fact 5.1 might be the most useful of the bunch, saying that every function is in big theta of any constant multiple of that function. So like n is in big theta of 2n, n squared is in big theta of 5n squared, n is in big theta of 0.00000001 n. Constant multiples don't change the asymptotic growth rate. And you can use this fact, which applies for any constant c greater than 0, with the constant c equals 1, to say that every function is in big theta of itself. Obviously, everything is equal to itself. And that usually gives us a really nice starting point for proofs like these. Once you've pointed out that a function is in big theta of itself, there's a lot you can infer from that. Such as how the thing we've already proven about how n cubed is in big theta of itself implies that n cubed is in big omega of itself. Excuse me. As you might have guessed from the small text on the slides, it's very helpful with these facts to compare them to how numbers work with their inequalities. Big theta being equivalent to big O and big omega might not be immediately sensible, but that thing you're told to compare it to makes sense if you think about it. If x is less than or equal to y, and x is greater than or equal to y, well, you know that x can't be simultaneously less than and greater than y. So the only way for that to work is for x and y to be the same number. Likewise, f can't grow both more quickly and more slowly than g. So the only way for it to work out when both of those are true is for f and g to have the same asymptotic growth rate. So n cubed is in big omega of itself. And then we use fact 4.2 to say that n cubed plus 1 is in big omega of n cubed, which might strike you as weirdly simple considering the last time we tried to compare functions where we had a plus 1 term. We had to say, well, like any constant is less than a logarithm, and any logarithm is less than a polynomial, therefore the constant is less than a polynomial. But here we can just add a constant, who cares? Why? Well, remember what big omega is. N cubed is basically greater than or equal to itself. So like, if we already have a statement like this, you could just add 1 to the big side. It's still true. And of course, remember that we're not dealing with inequalities like greater than or equal to. I'm only mentioning them as like a conceptual aid to help you understand asymptotic notation. Please don't get those mixed up on assignments and quizzes. So yeah, just like how you can just add anything you want and anything positive that you want to the big side of an inequality of numbers, adding any function to a function that already grows faster than something else just makes it grow even faster. So we don't need any restrictions on the thing we're adding. G in fact 4.2. On the other hand, if f was growing slower than h, and we wanted to add something to f and make that sum still grow slower than h, we'd have to impose some rules on the thing we're adding, just in case their sum ends up too big. Now we're going to show that n squared is not in big theta of n cubed. So we're going to use that bit of the hierarchy of functions again. We know that n cubed is in little o of n squared is in little o of n cubed. And then if you use 3.6, to say that it's not in big omega. As always, the relationships between these like random letters, some of which are Greek, others are Latin, may be unintuitive, but you should keep in mind the comparisons with numbers and their comparators. If x is strictly less than y, then x is less than y. It's not equal to y, and it's definitely not greater than y. So we can say for sure that x is not greater than or equal to y. With their equivalents with functions as n goes to infinity, if f grows way more slowly than g, we know that it doesn't grow at least as quickly as g. So n squared is not in big omega of n cubed. And then we have that if and only if alternate definition of big theta. F is in big theta of g if and only if it's in both big O and big omega of g. We just showed that it's not in big omega. That is, n squared is not in big omega of n cubed. So since it's not in big omega, and big theta requires both big O and big omega, we can conclude that n squared is not in big theta of n cubed. Ooh, logarithms. So we're going to show that n times log base 3 of n is in little o of n cubed. So we start off with the fact that is hopefully being drilled into your heads right now. Any logarithmic function is strictly smaller than any polynomial. So we do that with log base 3 and n. And then also we use the hierarchy as it pertains to polynomials to say that, I can keep underlining things now. N is in little o of n squared. And then it follows from the fact that it's in little o of n squared that it's in big O of n squared. Remember that thing I ranted about in the first or second lecture about how something being less than something else implies that it's less than or equal to something else just because of how OR statements work? Well, same thing applies here. And you can see that little o implies big O from their definitions. Proving that something is in little o requires showing that it works for all m. And once you've shown that it works for all m, that implies that it works for any m, the existential quantified version, a specific m. Excuse me. So whatever. N is in big O of n squared. And now the choices of functions and asymptotic notation may have seemed arbitrary. It's probably not clear right now why we showed that one function is in little o of n and the other big O of n squared, but it was all for the sake of setting up the use of fact 5.4. If so for functions f1, f2, g1, and g2, then if f1 is in little o of g1 and f2 is in big O of g2, then f1 times f2 is in little o of g1 times g2. Cool. It's a product rule. These specific bits of notation in the if part, like one function being in little o and the other being in big O, are basically there to support the definitions for reasons that are similar to the stuff you'll do in that bonus question in the last assignment if you're not completely dead by then. But for now, we can just take it for granted. Fact 5.4 just works. So we found log base 3 of n is in little o of n, and that n is in big O of n squared. So with that fact, log base 3 of n times n is in little o of n times n squared, which is then cubed, which is what we want. Exponential functions. As I sort of alluded to in a previous example while we were doing definitions and stuff, a similar hierarchy applies to exponential functions as they do to polynomials. So we're going to see a fact that says, like, if a is less than b, then a to the n is in big O of b to the n, or something like that. Fact 1.4 may look very similar to 1.3. I know I had to take a second to focus on this and go like, isn't that the same thing? But it's not. Notice that instead of n to the power of a being in little o of n to the power of b, it uses n to the power of a being in little o of b to the n. So it's a different type of function inside of the notation. Moreover, the relationship between a and b doesn't matter here. Something like n to the power of 1,000,000 is still in little o of 2 to the n, or 3 to the n, or 999 to the n. No matter what, regardless of the exponents, a polynomial will grow more slowly than an exponential function. Actually, I'll keep it here. It's a worthwhile example of fact 1.4. So then by 5.1, 2 to the n is in big theta of itself. That's just that constant multiple thing again, but with the multiple in question being 1. And then, since big theta is equivalent to both big O and big omega being true at the same time, we can say from the fact that 2 to the n is in big theta of itself, that 2 to the n is in big O of itself. And then we apply that strange product rule with big and little o. So on one side you have n times 2 to the n. On the other side you have 2 to the n times itself equaling 4 to the n. And you get the conclusion that we want. N times 2 to the power of n equals, or is in little o of 4 to the n. With 5 minutes left, I'm not going to let you go early this week, but I'm going to flip through the remaining examples and see which one is going to be the most useful to go through. Oh, excellent. After this, we're just doing general asymptotic properties again. So like that's bonus question, the last assignment type stuff. So I'm just going to do this last example that has to do with specific functions, and then we'll go. Where'd I go? Oh. So n squared plus 1 is in big theta of n squared. So like adding 1 to n squared doesn't change its asymptotic growth rate. So we're going to use that fact about big theta being an if and only if statement. This will probably come up a lot, by the way. So we're going to prove separately that n squared plus 1 is in big O of n squared, and that n squared plus 1 is in big omega of n squared. So to show that it's in big omega, we start with the fact that n squared is in big theta of itself. Oh wait, I was getting ahead of myself. To get a start on both of those separate proofs, we use the fact that n is in big theta of itself, which means that it's in big O and big omega of itself. Then we use our sum rules to go from the fact that n squared is in big O and big omega of itself to go to the fact that n squared plus 1 is in big O and big omega of n squared. For big omega, adding 1 just immediately results in what we want. Remember that this works similarly to how it does for numbers. N squared is already greater than or equal to n squared, so adding 1 will just make it even more greater than or equal to. But then doing the same thing with big O, so-called less than or equal to, requires you to justify that adding that extra 1 won't make the resulting function start growing faster than n squared. So we use a similar sequence of like implications to previously, like I think this was the first example on this slide deck. Any constant is in little o of a logarithm. Any logarithm is in little o of a polynomial. Therefore, constant is in little o of a polynomial. We used log base 2 here, but it doesn't matter. The theorem, or the use of the fact would have worked for any log base. So now that we have those two relationships with n squared and 1 to n squared, we can use fact 3.4, the addition rule. Oh wait, no, there's one more step, just showing that 1 is in big O of n squared. Then after that, we can use the addition rule for big O and little o to show that n squared plus 1 is in big O of n squared. And then I don't really like the lack of conclusion on this, although I guess I understand the space constraints of these slides. I think it would have been nicer if it said something like, we have thus shown that n squared plus 1 is in big O and little o of n squared. By step 1, we have shown that n squared plus 1 is in big omega of n squared, as required. And then you draw a little square at the end. Oh, that's a gross square. Then you draw a nice square at the end to show that you're done. And that we're done too. Assignments due on Friday, so keep working hard on that, and I'll see you all on Monday.